Representation of functions by power series. So in this section, we're going to be learning how to represent certain types of functions as sums of power series by manipulating geometric series or by differentiating or integrating such a series. You might wonder why we would ever want to express a known function as a sum of infinitely many terms. Well, as you're going to see later, this strategy is going to be useful for integrating functions that don't have elementary primitive functions. Uh, it's going to also be useful for solving differential equations and also for approximating a certain class of functions by polynomials. Okay, to get started, let's start by recalling the following result. This dates back to section 9.2. One of the examples, to be more precise, it's example 6. We realize that this series, whose terms are xn, is a geometric series, and hence it's going to converge precisely when um, the absolute value of its common ratio, which is in this case x, is smaller than 1. As such, it's going to converge, and its limit is going to be the first term, which is 1, right? The first term is 1, divided by 1 minus that common ratio, which is x. Okay, so this is something we developed, and let's refer to it as musical note here. So this is something we know, and in this section we're gonna look at it from a different point of view. We're gonna regard it backwards. We're gonna say, okay, I have this function then, which is 1 over 1 minus x, and I can represent it as, or I can express it as a power series centered at 0 in this case, right? So this function can be represented by this for all such x, for all x which are between -1 and 1. All right, so here's an example. Example 1. Express 1 over 1 plus x squared as the sum of a power series centered at 1 and find the interval of convergence. So the structure of this function, you can't help but just realize that this is of the same structure as this function, correct? Ignore what this x is. Just think about it as an s or a star here. Okay, so it's that star, and this is the star, right? Just ignore these guys. So 1 over 1 minus a star is equal to the series whose terms are the star to power n, and this is gonna be true for all as long as you replace the star by a number between -1 and 1. Okay, so in this case, who's the star? Who's the star? It looks like the star is gonna be -x squared in this case, right? Because of the presence of this minus. Okay, so let's take it here. So example 1. So example 1, we have that this function 1 over 1 plus x squared, I can regard this as 1 over 1 minus the -x squared. Why? Because I want to make it closer to this structure, right? Now I'm gonna employ this musical note over here. So we're gonna now employ the musical note. I'm gonna employ it with the choice of the star being -x squared, right? And as such, what do we get? So we get that the series, we get that this function is equal to the series of that star to power n, as long as the star is between -1 and 1. So we get that this is equal to the series that starts at 0 of the star, and as we said, the star is that -x squared in this context, okay, to power n. And this is true as long as, so this is true for all x, or for all -x squared, an absolute value smaller than 1, correct? And what does this mean? This means that well, this is the same as x squared, right? Because that guy, the absolute value of -1 is 1, and the absolute value of x squared is x squared because x squared is non-negative, less than 1, which means that x in absolute value is less than 1, right? This is when this happens. They are the same. Okay? You can think about it by just anyway, taking square root or okay. So and what does this mean? What does this mean? This is equal to summation. This is -1 to power n times x to power 2n. Am I correct? Minus x squared is the same as -1 times x squared, and -1 x squared to power n is -1 to power n, so we get this, times x squared to power n, and x squared to power n is x to power 2n. You multiply the powers, right? So we get this. So this function 1 over 1 plus x squared can be represented as a power series centered at 0. And that power series has terms -1 to power n, x to power 2n. Okay? And the interval of convergence, we discovered this means that x is between -1 and 1, right? So x means between -1 and 1. Okay? So this function and this series are the same as long as x is between -1 and 1. Okay. 2. Example 2. Express 1 over x as the sum of a power series centered at 3 this time. It has to be at 3. Remember, what does it mean to be at 3? It means that I want to rewrite this as, the series whose terms are, I don't know, Cn times x minus 3 to power n, correct? And I want to discover what these Cn's are. Make sense? So this is what we mean by, if you remember, this is what it means by definition, what it means that the series is centered at 3, correct? Okay, so I want to rewrite it as such. All right, let's do it. So let's take that problem, example 2. So I have 1 over x, and as we said, we want to rewrite it as such. And the only thing that we can use technically at this point, the only tool that allows us to transition from a function to a series is this musical note, right? That's the only connection up to this point that we have. Okay, so I want to rely on this. I would like now the start to be something of the form x minus 3, right? I would like the start to be of the form x minus 3, correct? So I want to cook up an x minus 3 over here. All right, how do we do so? Obviously, try it on your own first. The way I'm going to look at it is, in order to create it, how about we add a 3 and subtract by 3? Okay, so how about we add a 3 and subtract by 3? So how about this? So this is the same as x, right? 3 minus 3 is 0, and this is x. Okay, why this is useful? Because I can rewrite this as 1 over, I can factor out 3 now, and I get 1 minus 3 minus x, correct? Over 3, sorry, over 3. You agree with this? So I get that one. And now, okay, so I can push that 1 over third by itself, and then 1 over 1 minus 3 minus x over 3, correct? So I can think about this as being the star now. I can think about this as being the star, this quotient, because I have this x minus 3 or 3 minus x. We'll reverse the order later, but this difference is desirable because I would like to have a series centered at 3 as discussed. So I would like to have a term that looks like this, x minus 3, and I have it. I see x minus 3, right? Okay, so I'm gonna use the musical note now. 1 over 1 minus star. I'm gonna use star, as we said, as being this 3 minus x over 3. So I'm gonna get that one where the star is the chosen one. Okay, So this is where the musical note is gonna kick in. Oops, we keep the pink. So this is where the musical note is gonna kick in, and it's gonna kick in with the star being that guy, right? Okay, and what do we get? That 1/3 is innocent, so it remains here. And that one is by the musical note. This is the summation, and starting at 0. The star, which is that guy, to power n. And this holds as long as the star in absolute value is less than 1, right? This is what the musical note tells us. This holds as long as the star in absolute value is less than 1. So this is true as long as, so for all, how about I put it here? For all on x such that 3 minus x over 3 in absolute value is less than 1. This is what it means that the absolute value of the star is less than 1. Agree with this? Okay, and what does it mean for x? What does this mean for x? Because we would like to find, as we said, the interval of convergence. We would like to find the interval of convergence. So we would like to find, we would like to put conditions on x so that I get a ball centered at 3 and of radius, whatever the radius is. That ball is gonna be, no matter what number you choose in that ball, I'm gonna have convergence of the series, and it's gonna be converging to 1/x, correct? Okay, so what does this mean in terms of x minus 3? This means that the absolute value of 3 minus x is less than 3, right? If you multiply both sides by 3, because absolute value of 3 downstairs is 3, so if you multiply by 3 you get this. And obviously this means that, what does this mean? This is, first, this is the same as x minus 3 less than 3, right? The absolute value of a minus b is the same as the absolute value of b minus a, so you get that. And this is equivalent to x minus 3 between, so x minus 3 between minus 3 and 3, which means x between 0 and 6. You agree with that? Which means x between 0 and 6. Because this means that x minus 3 is between, how about I write it for you? So this means that x minus 3 is between minus 3 and 3, right? This is what this means. And then if you add 3 to all sides, you get that 0 is less than x less than 6. Okay, so that's the interval of convergence. That's the interval of convergence. How about we call it IOC? Okay, interval of convergence. Very good. Let's clean up this writing a little bit. Make it closer to this, right? Let's clean it up. Well, that's the same as 1/3. That's the same as 1/3 times the series that starts at 0 of 3 minus x is the same as minus 1 times x minus 3, right? So that's the same as minus 1 to power n times x minus 3 to power n divided by 3 to power n. Agree with me? Do you agree with this? So one more time, 3 minus x is the same as, let me write it for you. So 3 minus x, that guy, that's the same as minus 1 times x minus 3, right? Because this is the same as minus 1 times x, so minus x. Minus 1 times minus 3 is plus 3. So these are the same. And now raise it to power n. You get minus 1 to power n. It's right there. X minus 3 to power n, right here. Divide by 3 to power n. There, right? Okay. Now if you want to bring in that that 3 here, you get what? You don't have to, but my point is, let's clean it up a little bit. So you can get summation that starts at 0 minus 1 to power n divided by, if you bring in this 1/3, so 1/3 times 1 over 3 to power n is 1 over 3 to power n plus 1, yes? Okay, times x minus 3 to power n. Okay, and this is the series representation of this function 1 over x, power series centered at 3 that represents 1 over x. Make sense? And they are the same as long as x is between 0 and 6. Okay, this is the interval of convergence that the question was asking. Make sense? So we were able to write it as such, and the Cn at the end of the day turned out to be minus 1 to power n divided by 3 to power n plus 1. Okay. All right, another one, example 3. Find a power series centered at 0 this time. So centered at 0, which means I want to rewrite this as something like this, right? Correct. So I would like to write it as such. Okay. And we want to determine the interval of convergence of the power series centered at 0 that represents 1 over x plus 2. Okay. All right. So let's go to the next page so we can have more room. So that's example 3. And here we want to find a power series centered at 0 representation of this function 1 over x plus 2. So certainly I want to use the musical note result, because that's the only way I can represent, that's the only result up to this point that I know of that allows me to represent a function as a power series, correct? So the question is, what should be that star? Okay, so the question is, what should be that star? Let's go back to that page. So I have here 1 over x plus 2, and clearly this can be thought of as 1 over 2 minus the minus x. Agree with this? Okay. And that's equal to 1 over 2 times 1 over 1 minus the minus x over 2. Okay. So now it is it's the same structure as this, 1 over 1 minus star. So now I can employ that musical note result. And as such, what do I get? Who's the star here, by the way? Who's the star? The star is this. That's the star. So I'm going to write then, by the musical note result. So by the musical note result, I have 1 over 2 times the series that starts at 0. And here I have, if you recall musical note, I have the star to power n, right? And who's the star again? Minus x over 2 to power n, right? So here I transition to a power series representation of this, and this is centered at 0. So let's probably make it look a little nicer. So that's, or make it closer to the form sigma cn x to power n, right? So the question is, what's cn? So we have here minus 1 to power n x to power n divided by 2 to power n plus 1. Correct? Because it's the same as before. So 2 to power n times 2, and 2 to power n times 2 is 2 to power n plus 1. So we get this. And don't forget, this holds, the musical note holds as long as star is an absolute value less than 1, right? So that's going to be for all x such that the absolute value of that star is less than 1. correct? And what does this mean? If you unravel what this means, what does it mean that the absolute value of x over 2 is less than 1? This means that the absolute value of x is smaller than 2, right? Which means that x is between -2 and 2. So that's the interval of convergence, right? So that's the interval of convergence, IOC. Okay. All right. So how can we summarize this? This function can be represented by this series, which is a power series centered at 0, for all x in between -2 and 2. All right, let's go back to the previous page and go for the next example. Example 4. Find a power series centered at 0 for this function, x minus 7 divided by x squared plus x minus 2, and determine its interval of convergence. This function here doesn't look like the previous ones. It doesn't look like this, right? This is a second degree polynomial downstairs. And it doesn't look like any of the previous ones. It doesn't even look like this, correct? I hope you take a moment to pause this and think about it for yourself. What we're gonna be doing is I'm gonna factor this denominator, this second degree polynomial, and once you factor this, I mean, you can factor it here because the discriminant, as you can compute the discriminant here is non-negative, right? And as such, I can factor that guy. Once you factor it, you're gonna have linear factors. Each one is gonna look like this, right? Something like this, which is something we can handle using the musical note result because we've already done it. And how about then using partial fraction decomposition to get to something similar to this? Okay. All right. So I'm just designing a plan here. That's it. All right. Let's do it. Let's do it here in this this room here. So x minus 7 divided by x squared plus x minus 2. If you factor the guy downstairs, you can factor it as x plus 2 times x minus 1, correct? And upstairs is that x minus 7. Now we're gonna use partial fraction decomposition. Let me zoom in so you can see it better. So now we're gonna use partial fraction decomposition here to rewrite this as something over x plus 2 plus something over x minus 1. Remember the partial fraction decomposition? All right. So it turns out that this thing that sits in the numerator is 3 here, and the guy that sits here is -2. Okay. All right. So this one here is 3 times 1 over x plus 2, right? This is the same as 3 times 1 over x plus 2. Correct? 3 times this. Okay. And 1 over x plus 2 is something we've already done. So that power series representation centered at 0. So representation of 1 over x plus 2 was done in example 3. So I know how to handle this part. How about this part? Well, this is very, very close to 1 over 1 minus x, the left-hand side of the musical note, right? Remember the musical note, 1 over 1 minus star? That's very much the same as this. How about pushing a minus and factor downstairs and combining it with this minus? So that's what I mean. How about writing this as 3 times 1 over x plus 2? Okay, so let me rewrite it just for completion here. Let me just write it first as such. And then, as we said, this guy, I'm going to write it now as -2 over 1 minus x with a minus sign. Okay, and then this minus and this minus are going to cancel each other, correct? So this minus and this minus are going to cancel each other, and then I'm going to get this. Do you agree with me? Okay, and by example 3, So example 3. What's the power series representation centered at 0 representation of this guy? Well, we've done it here below, right? It's this guy. So I'm gonna take this guy and copy it. Okay. So that's gonna be then 3 times the series that starts at 0 minus 1 to power n divided by 2 to power n plus 1 xn. Okay, so that's the power series centered at 0 representation of 1 over x plus 2 plus 2 times the power series representation of 1 over 1 minus x. So I'm technically saying, okay, let's push that 2 here, have a 1, correct? And that 1 over 1 minus x by the musical note, so I'm also using musical note by itself, even though it's embedded in example 3. I'm using it for the second part, and I can rewrite this as the series that started at 0, x to power n. Agree with this? Okay. Now you can. This is obviously a convergence series for an appropriate x. How about we know or we understand what the interval of convergence for each one is? What's the interval of convergence of this series? Well, this was computed before, right? That was a minus 2, 2. Correct? So the interval of convergence of this series was minus 2, 2. And how about the interval of convergence of this series? Well, this is minus 1, 1. This is on the first page. This is on the first page, minus 1, 1, right? As long as the guy sitting here is between minus 1, 1. And the guy happens to be x in this case. Correct? Okay, so the interval of convergence of this guy is minus 2, 2. The interval of convergence of this guy is minus 1, 1. Okay? And for an x in the intersection of these intervals of convergence, why intersection? Because you want both series to converge, right? You want both series to converge because I'm talking about sum. And this sum, the sum of the two series happens to be this function. So this function is equal to the sum of series as long as x makes this series convergent and this series convergent, which means x should be in the interval of convergence of this guy and interval of convergence of this guy. So x has to be between minus 2, 2, and it has to be between minus 1, 1. Make sense? So let's write this. So the interval of convergence is the intersection between minus 2, 2 and minus 1, 1. Why? The interval of convergence of this whole thing is equal to the intersection between the interval of convergence of this and the interval of convergence of this, as we said before. Okay, so the x has to make this converge and this converge. This is the and part, the intersection part. And what's this intersection? What's minus 2, 2, minus 1, 1? What's the intersection? What are these guys that live in between both of them? It's everybody between minus 1, 1, right? Because this is a smaller set. If you intersect a set with a bigger set, the intersection is the smaller one, right? Okay, so the interval of convergence is minus 1, 1. Make sense? Okay. So they want a power series centered at 0. This looks like two power series centered at 0. We want just to write it as one power series. So we want to write this as with one summation. And we know we can condense. Why? Because it's one of the properties that we mentioned earlier, because each one of them converge for such an x. For such an x, both of them converge, and as such, I can take the sum of the series as being the series formed by the sum of the terms, right? So what I'm saying is the following. How about I shrink this a little bit? Let's shrink it a little bit, so let's write it here. And then this is equal to the series that starts at 0. The Cn, I have to determine xn, right? Correct? And what's the Cn? What's the guys that sits here? Well, it's gonna be 3 times negative 1 to power n divided by 2 to power n plus 1. So it's gonna be 3 times minus 1 to power n divided by 2 to power n plus 1 plus 2 times xn. Well, xn is in factors, so plus 2, and that's it, right? Makes sense? So let me drag this for you here. Okay. So I condensed because each series converges, and we know, as we said, the sum, a constant multiple of a convergent series is the same as the series formed by this factor times the terms of the series. You can push that 3 inside, that's what I'm saying, and the 2 as well. And as such, you get 2 series which converge, and the sum of these 2 series is the same as the series whose terms are the sum of the terms of the previous series, right? Of those 2 series. So we get like this. And if you factor xn outside, you get this. Okay? So the series starts at 0 and it's infinity, right? Okay, so that guy, that series is going to be at the end of the day a power series centered at 0 representation for this function, as long as x is between minus 1, 1, right? Don't forget this, as long as x is between minus 1, 1. Okay, moving on. Example 5, find a power series centered at 0 for this function, x cubed divided by x plus 2, and determine its interval of convergence. Okay, well, that's easier than the previous one. Well, x cubed divided by x plus 2 is the same as x cubed times 1 over x plus 2, right? And by example 3, I know how to write, I know the power series centered at 0 representation of 1 over x plus 2, correct? So by example 3, I know how to write, or what the power series representation centered at 0 of 1 over x plus 2. It's technically this guy, right? So I'm going to copy that. So that's going to be x cubed. It's going to still outside. Sigma, n starts at 0 all the way to infinity. Minus 1 to power n over 2 to power n plus 1 xn. Okay. So I have this. And now this x cubed is independent of n. So that it's a constant with respect to n. I can push it inside. And if you push it inside, what do you get? The x's are going to pile up. So x to power n times x cubed is going to be x to power, you add the powers, so 3 plus n or n plus 3, right? So you get the series that starts at 0 all the way to infinity, minus 1 to power n divided by 2 to power n plus 1 times x to power n plus 3, correct? So we get that. Okay, now if you insist in writing this as an n, not as n plus 3, this is a correct answer, okay, no doubt. But you can rewrite this whole thing with a power here, with a clean power, and by clean I mean instead of shifting that n by 3, how about having 1n, or another, another name for that exponent? How about k for a power? So how about doing a substitution as follows? How about renaming n plus 3 to be k? Okay. Why? Because if you do so, my point is, again, you don't have to. My point is, if you insist in writing this as the series something here, x to power k, clean power, as opposed to n plus 3, how about renaming n plus 3 to be k? Okay, As such, this becomes k. And how about that? This becomes minus 1 to power, what's n in terms of k? Well, if k is n plus 3, then n is k minus 3, right? So this guy upstairs becomes minus 1 to power, you don't need these parentheses, let me just eliminate them. To power k minus 3, right? You agree with me? This n, if k is n plus 3, solve for n is k minus 3, so I can represent n by k minus 3. And downstairs becomes, if n is k minus 3, right? If n is k minus 3, what's n plus 1? So if n is k plus 3, n plus 1 is going to be k minus 2, right? So that guy is going to be 2 to power k minus 2. Okay? And now, how about this index, k? Where does it start? If n used to start at 0, k is going to start at 3, no? K is going to start at 3, and since n is going to blow up, k is going to also blow up. Make sense? So you can rewrite this as this. If you insist on having this exponent as being a clean exponent. You don't have to all the time, but just in case you need to. Okay? Now, one last comment here. I can, since k is a dummy letter, after the fact, right? After the fact, since k now is a dummy letter, if you ignore all this part and you just focus here. If you just focus here, since within this environment, k is a dummy index, right? You can call it k, m, p, t, whatever you want. And hence, you can call it n. You can call k to be n and rewrite this whole thing as, let me write it in different red color. You can rewrite this as n, actually different color, brown. So after the fact, you can rewrite k as n and get n here, n here, n here, and n here. If your favorite letter for index is n, that's what I'm saying. You can rename, after the fact, you can rename k to be n and get this. Okay? So you can read it as the series indexed by n, and n starts from 3 all the way to infinity, of the term that looks like minus 1 to power n minus 3 divided by 2 to power n minus 2 times x to power n. Okay, so that's another way of writing this series. If you don't care about the index name, let's just keep it k. Okay. All right, let's see this next comment. The sum of a power series is a function, right, f of x, can be thought of as a function as we've been talking about, whose domain is the interval of convergence of the series. So it's the set of all the points that allow the series to converge, and that set was referred to as the interval of convergence. And what we would like to do is we would like to be able to differentiate and integrate such functions that are given by power series, or that can be represented by power series. And the next theorem, which we will not prove, is going to tell us that we can do so by differentiating or integrating each individual term in the series, just as we would do for a polynomial. Okay, this is called term-by-term differentiation and integration. Let's read the theorem. So it goes like this. If the power series sigma n cn x minus a to power n, so this is centered at a, has radius of convergence r, that's positive, then the following, then the function defined by being the power series is differentiable and hence continuous on the interval centered at a having radius r, right? So a minus r to a plus r. Moreover, not only we know that it's differentiable, we also know that its derivative is gonna be technically differentiating. Look, it's the same as differentiating term by term, right? What's the derivative of c0? It's 1. 0, right? So this guy is gone. You don't see it. What's the derivative of c1 times x minus a? it's c1. So you get this. And the derivative of this with respect to x is 2 times c2x minus a, and so on and so forth. So this is what we said in the previous comment. You can differentiate a power series term by term. And if you put them together, you're talking about this as being the derivative of this guy, correct? So what one is saying is that if you differentiate with respect to x the series cnx minus a to power n, that's the same thing as taking the series whose terms are the derivative with respect to x of those guys. Make sense? Because the derivative of those guys is n cnx minus a to power n minus 1, correct? So that's what we mean term by term. So you just differentiate exactly as you would do for polynomials. Okay. Furthermore, you can integrate term by term as well. You can integrate term by term. Okay. So you integrate that guy is the same as integrating term by term as you do for polynomials. So if you were to integrate this series, which is the power series centered at A, what this theorem is telling you is that you can do, this is the same as the series that starts at 0 of the terms that look like the primitives of the earlier, the initial terms, right? Okay, let me put those brackets here. Okay, so what these two colored comments, they assert for us that the same is true for infinite sums, right? And by the same, I mean what we used to do at the level of polynomials, finite sum, we can still do at the level of infinite sum, provided obviously we are dealing with power series, For other types of series of functions, the situation is not as simple. Okay, so if you have a function that's not represented by power series, you cannot do this all the time. Okay, you're gonna have some conditions in order to do that. All right, so but in this section we're only dealing with power series, and for power series you can handle them, you can differentiate them, and you can integrate them the way that we used to do for polynomials, and by this I mean term by term. Okay, the last comment, or the last part of the theorem, it says the radii of convergence of the power series in equations 1 and 2, so in those two guys, are both R. And what's R? It's that radius of convergence of the original series. Okay. Let's read the comment after the theorem. Although the previous theorem says that the radius of convergence remains the same, right? That's part of the conclusion of the theorem. When a power series is differentiated or integrated, this doesn't mean that the interval of convergence remains the same. Okay, so remember, the radius of convergence doesn't force that the interval of convergence be the same. It's of the same, the interval of convergence have the same radius, but the endpoints may or may not be included. Okay, so it may happen that the original series converges at an endpoint, whereas the differentiated series diverges there. Okay. All right, let's do an example. Let's do a three-part example here. Find a power series centered at 0, and this power series is a representation for each of the following functions, and determine its interval of convergence. Okay, let's look at part 1. 1 over 1 minus x to power 2. So this function, if you think about it, how is it connected to the musical note? Remember what the musical note is? the function, the musical note? How about we write it here? So the musical note was that if we have 1 over 1 minus x, how about thinking about x as a star? Then we can rewrite this as the summation of the series that starts at 0 of this star to power n, and this is for all values of the star that an absolute value is smaller than 1. Okay, so that's the musical note. So how is this related to that function 1 over 1 minus star? Remember, we can differentiate and integrate. Remember the theorem that we just proved, not proved, just discussed? It allows us to differentiate, or it tells us how to differentiate a series and how to integrate a series, and not any series, just a power series. Okay, so this theorem has to do with just power series. So what's the relationship between this and this? Do you agree that if you differentiate 1 over 1 minus x, do you agree that you get 1 over 1 minus x squared? And now, do you know a power series of 1 over 1 minus x? Yes, it's right there. This is equal to the derivative with respect to x of this series. Correct? And don't forget, this is as long as x is an absolute value less than 1. Okay. And once you differentiate this, oh, by the way, this is by musical note, right? Okay, and once you differentiate this, you get the power series representation of 1 over 1 minus x squared. And this power series is centered at 0 because we are starting from a series that we are differentiating a series or a power series centered at 0. Okay, so the previous theorem now tells us how to differentiate. So by the previous theorem, it tells that theorem tells us that you can differentiate term by term, and as such we get sigma d over dx, the derivative of xn. Make sense? Okay, and what's the derivative of this term, xn? So that's going to be the series n times x to power n minus 1. But here the series is going to start at 1, right? Why? Because the very first term when n is 0 this is 1. The first term in this series is 1, and if you differentiate 1, that's 0. So the very first term that's going to be non-zero is this guy when n is 1. Okay, so this is part of the theorem, right? I mean, the derivative of the function is going to start at 1. Okay, that series starts at 1. Okay, so we get this. And if you don't like n minus 1, you can do exactly as we did before in the previous problem. You can rename n minus 1 to be k, right? You can rename n minus 1 to be k, and as such this series is equal to the series whose terms are, if n minus 1 is k, then n is k plus 1, so that guy is going to be k plus 1 times x to power k, since we are doing the following substitution. N minus 1 is k, and if n starts at 1, k is going to start at 0, right? If n starts at 1, k is starting at 0, and if n, I mean, it's gonna go to infinity by an increment of 1 each time, so k is also going to infinity. All right, so we get this power series centered at 0, that's representing 1 over 1 minus x squared. And this is for any x, as we said, this is for over here. This is for any x less than 1, right? An absolute value, which means this is for any x between -1 and 1. Correct? So the interval of convergence remains 1 according to the theorem. According to the theorem, the interval of convergence is going to remain R, and R is the interval of convergence of this series that's representing the function f, correct? So we're talking about f being 1 over 1 minus x here. That's the f of the theorem, and that's f prime, right? So the interval of convergence for this series, which is this, right? The series representing f, which is this guy. The interval of convergence is minus 1, 1. So the radius of convergence is 1. Here I'm going to still have radius 1 for the f prime function, for the series representing f prime. I'm going to still have interval of convergence. The radius of the interval of convergence is 1. Okay, so I get this. Now the question is, for which x among these endpoints, or does there exist any of the endpoint that allow the series to converge? Let's start with 1. If you take this upper endpoint, which is 1, replace x by 1 here, you get 1 here. So the terms of the sequence become, the terms of the series become k plus 1. And as k go to infinity, k plus 1 goes to infinity. It doesn't go to 0. As such, this series, when x is 1, is not going to converge. Similarly, when x is negative 1, right? If x is negative 1, this is going to become minus 1 to power k. And that series is going to, or those terms are going to contain terms that go to infinity, especially when k is an even number, right? So it's going to go to infinity. And as such, those terms do not go to 0 as k goes to infinity. So when x is negative 1, that series is going to diverge. So when x is negative 1 and when x is 1, the series is diverging. So this would be the interval of convergence here. Okay. Part 2. Let me draw a separation between the parts. Let's go to the second one, ln of 1 plus x. How is this related to 1 over 1 minus star? Well, if you take the primitive, first of all, understand that they told us ln of 1 plus x. So the provision to this expression is that x is bigger than negative 1. Do you agree with me? Because if x is less than or equal to negative 1, this becomes 0 or less. Correct? So you need 1 plus x to be positive for the log function to be a meaningful thing. Right? Log doesn't operate on non-positive entities. And this guy is positive as long as x is bigger than negative 1. So this is the provision of that expression. They told us that x is bigger than negative 1. All right. As such, if you integrate the function 1 over 1 plus x, what do we get? If we integrate the function 1 over 1 plus x, under this condition, you get ln of 1 plus x, right? Correct? Forget about the constant for the moment, because I'm going to pick up the constant on the new side, on this side. You agree with me? So technically I should put the bars, right? But since I'm talking about x being bigger than negative 1, then that's the same as putting the parentheses. Okay? All right. And then this becomes the primitive of the power series representation of 1 over 1 plus x. Now what's the power series representation of 1 over 1 plus x? It's very similar to this, but the star is negative x, right? The star is negative x. So that's going to be sigma n starts at 0, from 0 to infinity, minus 1 to power n xn. Correct? So here I thought about the star as being negative x, to just inject that minus. So we get that, dx. And by the previous theorem, obviously here I used musical note. Keep in mind, that I can use the musical note as long as the negative x in absolute value is smaller than 1, right? So here I'm talking about x being in absolute value smaller than, an absolute value is smaller than 1, right? When negative x or x is the same thing. Okay. All right. Let's integrate. So by the theorem, it tells us, or the theorem tells us, that this is the same as the series from 0 to infinity of the integral of minus 1 to power n xn dx. And now we're gonna integrate. So if we integrate this, we get sigma n starts at 0 all the way to infinity, minus 1 to power x to power n plus 1 divided by n plus 1 plus a constant of integration, right? A constant of integration. And don't forget that this is true for the same radius of convergence as the original one, which is the series minus 1 to power n xn, which means we're talking about the interval minus 1 1 still, correct? So we're still talking about this. Again, by the theorem, f prime and the primitive of f, they share the same radius of convergence. The radius of convergence here is negative is 1, correct? The radius of convergence is 1 here. Okay. The interval of convergence is centered at 0 and of radius 1. Okay. The only change may happen at the endpoints. We'll check the endpoints at the end. All right. So what is that c? The c is a constant of integration, but we know what the function is. The function is ln of 1 plus x, so we can determine what the c is. How about we replace, since this holds for any x between minus 1 and 1, a good point between minus 1 and 1 is 0. How about we replace x by 0? So if we replace x by 0, so replacing x by 0, yields the following. ln of 1 plus 0. What's ln of 1 plus 0? That's 0, right? On one side, this is 0 because it's ln of 1. On the other side, we know that this guy is equal to this series, correct? Replace x by 0. That becomes sigma n starts at 0 all the way to infinity, minus 1 to power, I forgot to write the power n here, minus 1 to power n, x to power n plus 1 over n plus 1, plus c. Oh, I forgot also to rewrite or replace x by 0. We get 0 here, right? Okay, and what's this sum? This is a countable sum of 0. Each term is 0 now, right? It's a countable sum of 0, so this guy is 0. Okay, so what's the value of the right side then? It's c plus 0, so it's c, right? And as such, what's c? C is 0 then. So c is 0. So we can conclude up to this point, we can conclude that ln of 1 plus x is equal to ln of 1 plus x is equal to the series where c is 0, Okay, so it's going to equal to sigma n from 0 to infinity minus 1 to power n xn plus 1 over n plus 1. Again, if you want to rename n plus 1 to bk, be my guest and do it. Okay, I'm going to keep it like this. And this is for any x in absolute value less than 1. This is for all x in absolute value less than 1. Which means for all x between negative 1 and 1, right? Okay. Now, the question is, what's the interval of convergence of this series? I know up to now that the two functions, the series and ln of 1 plus x. These two guys are the same for any such x. For any such x. Now they told us for which x this series converges, and hence the name, and hence they called it interval of convergence of the series. So what are the x that allow the series to converge? Well, I know that as long as it x between minus 1, 1, the series is convergent. It's converging actually to this function, ln of 1 plus x. Now for the endpoints, what happens? If you replace x by this upper bound 1, if you replace x by upper bound 1, what do we get? We get minus 1 to power n. Let me actually write it for you. So when x is equal to 1, this series becomes this. Okay, I'm replacing x by 1. So I get this. And what do you know about this? This is an alternating harmonic series. This is convergent, right? This is convergent, which is convergent by the alternating series test, right? So you can run the test, the alternating series test. Remember, the alternating series, you want the an, or the, I don't know what we call it at the time, the 1 over n plus 1 to be a decreasing sequence that decreases to 0 eventually, right, as n goes to infinity, and obviously it does. So I have it. So I have convergence at 1. What does it mean? That series at 1 is convergent. On the other hand, how about when x is negative 1? So when x is negative 1, the series becomes, and by the series, again, I mean this, right? I mean this. You know what? Just for completion, let me write it. I'm not gonna write it. I'm gonna copy it. Okay. That series becomes sigma. I'm replacing now x by negative 1, right? And what do I get? I get minus 1 to power n minus 1 to power n plus 1 divided by n plus 1, which is the same as, what's that? Well, as n goes from 0 to infinity, either n or n plus 1, one of them is going to be even, and hence the other is going to be odd, right? So that product is always negative 1. So this is going to be negative 1 divided by n plus 1. Okay. All right. And this is a divergent series, right? This is a divergent series. This is the harmonic series. So which diverges. Correct. So negative 1 turns out to be a point that makes the series divergent, and 1 makes the series convergent. So what's the interval of convergence? So it follows that the interval of convergence of the series is negative 1 open, 1 closed, right? Makes sense? So at negative 1, the series turned out to be divergent. At 1, the series turned out to be convergent. And as such, we get negative 1 open to 1 closed, being the interval of convergence. The last part is arctan, and again, same question. I would like to write a power series centered at 0, representation of that function, arctan x. Okay. So part 3, arctan x. Well, how about, I mean, arctan x, how can I connect it to a function which I can represent it using power series. I'll center that 0 here. Well, the primitive of 1 over 1 plus x squared is arctan, right? Okay, and we know the power series representation of 1 over 1 plus x squared. This is an earlier exercise. It's this series, right? It's this one here. So we did this. This was example 1. Let me copy it actually and take it with me. And don't forget the radius of convergence is 1, right? So the interval of convergence is centered at 0 and having radius 1. Okay, so I'm gonna carry this information with me all the way to here. So this is equal to by example 1, right? This is by example 1. By example 1, this is equal to, let's paste that, this guy, dx, right? And there's an n missing here. Agree with this? So 1 over 1 plus x squared is the series. Don't forget the interval of convergence. Actually, the radius of convergence was 1 at the time, right? Okay. And now, by the theorem, I know I can integrate term by term. So this is where the theorem now kicks in. By theorem, I mean the previous theorem. And you can integrate term by term, and what do you get? You get sigma from 0 to infinity minus 1 to power n times x to power 2n plus 1 over 2n plus 1 plus a constant of integration, right? Plus a constant of integration. Okay, and don't forget this is for all x between -1 and 1. Okay, because we know that the radius of convergence of one or of this series, sigma n bigger than 0 or equal to 0 minus 1 to power n x to power 2n, that function, which is 1 over 1 plus x squared, they are equal as long as x is between -1 and 1. So the radius of convergence has to be 1 of the primitive, which is arctan. Okay, and the question is, what is c, right? What is c? Let's choose also, I mean, any number that's between -1 and 1 is going to reveal what c is. Let's take a good one. How about 0? How about 0? If you take x to be 0, for x equals 0, we get arctan, because arctan of x is the series for all x between -1 and 1. So for 0, I can plug in 0 here, and this is going to be equal to this series, -1 to power n, 0 to power 2n plus 1, divided by 2n plus 1, plus c, correct? Plus c. So these are the same, because again, this function and this function, which is a series, power series here, these two are the same for any such x, and this x certainly is between -1 and 1, so these values are the same. What's arctan of 0? Arctan of 0 is 0. And what's this left-hand side? Well, this guy is 0. It's countable sum of 0. So this is simply c, right? So this is simply c. So this is a nice c at the end. So c is 0, right? So therefore, arctan of x is equal to sigma -1 to power n, and this starts at 0, x to power 2n plus 1 divided by 2n plus 1 for all x between -1 and 1, right? For all x between -1 and 1. Now they said, what's the interval of convergence of this series? What's the interval of convergence of the series? So I'm gonna leave it, so interval of convergence, I'm gonna leave it as an exercise, and let's give a few words about it as an exercise. Look, we're gonna play the same game that we did many times before. Let's take x to be the upper bound, and let's take x to be this lower end point. If you take x to be this upper end point 1, that's gonna be 1, and then the series is gonna become an alternating series, minus 1 to power n divided by 2 times n plus 1. And this series is gonna converge when x is 1, right, by the alternating series test. So when x is 1, the series is going to converge. So 1 is going to be part of the interval of convergence of the series. And for -1, when x is -1 to power 2n plus 1, that's going to be an odd. 2n plus 1 is odd, so -1 to an odd power is -1 times -1 to power n. That's going to be also an alternating series, and you can run the alternating series test again, and you're going to also pick up the same conclusion, which is going to also be a convergent series. Okay, so long story short, the interval of convergence is going to be the closed set -1, 1. So -1 is going to be part of the set, the interval of convergence, and 1 as well. All right. Okay, so this completes this section.